Finding the elements of ship motion when replacing the control function with its expansion into a trigonometric series. Article number 12.10 of the book, Mechanical System Calculations of the Marine Facilities. Sometimes when we consider the issues of the ship keeping on the straight course by the control system, we have to adopt definite type of the control function for the simulation of the control system with feedback. For example, the simulation of the control function we can do with use of the trigonometric functions in particular. It can be a sinusoid, sinus function, or a cosine function. It depends on time. Yeah, we consider the processes. The variable is time t. But as well, we can use the non-analytical substitute of the control function. For example, here on the diagram 12.10.1, on the dependence on time indicated the optional optional type of the diagram of the turning rudder, the periodic diagram of the impulse type of rudder turning with amplitude of alpha rm. Alpha rm is the amplitude of the turn of the rudder for the objective to keep the ship on the straight course. But the function is not smooth with the brakes. So to substitute this into the right side of the inhomogeneous differential equation to get the decision of the equation, we can use the expansion of this nature of this pattern of the rudder turnings in time dependence. We can substitute this pattern by its expansion into, for example, trigonometric Fourier series. So we can use trigonometric Fourier series in the next this expansion of this impulse nature of the pattern of the rudder turning when it is substituted by the trigonometric Fourier series. We can next substitute this got expansion of this the impulse nature diagram. We can substitute this into the differential equation on the right side in the as the action of the controls patterns. And we will next have the decision if we substitute the control action as the expansion. They actually had having the impulse nature of the control action. When we substitute by expansion into the trigonometric Fourier series, we will have the decision of the inhomogeneous equation in as well as the expansion as a trigonometric series, because the functions of the dependencies in time, like a cosine function, trigonometric function, these functions are very convenient to use as the patterns of the expansion of the non-analytical nature or non-analytical shape of the diagram of the control action. We can unlimitedly integrate and differentiate the functions of cosine and sine. These functions are continuous and thus smooth. This is very comfortable to do the differentiation of the functions and the integration. The general type of the Fourier series we can indicate by the formula. This is trigonometric Fourier series with the real number variable x, just x. We will use t in the next, but first just about any variable of x. The Fourier series is the zero term of the Fourier series, alpha 0. Sorry, this is a0. Alpha will be the next when we will substitute the angle of the rudder turning. For the general approach, the trigonometric Fourier series has the form of summons alpha, A0, just any the first, the zero term of the Fourier series divided by 2 plus sigma, the total of the terms of n terms. Theoretically, this unlimited number of the terms from the first term, 0 we have here on the left in the first summand, and unlimited number n of the terms we can consider. It depends on how many terms we need to use in the expansion of the impulse nature function into the Fourier series. As many terms we have to consider and to count in the practical needs, so greater will be the accuracy of determination of the approximation of the function and determination of the decisions of the inhomogeneous any order differential equation linear with the right side as an inhomogeneous equation. If in the right side we substitute instead of the impulse nature or other nature non-analytical function, we apply the substitute by the expansion of this function into the trigonometric Fourier series. The coefficients of expansion into the trigonometric Fourier series are A0 is 1 divided by p multiplied by the integral from minus p to p. This is the usual formula. The function which expansion we consider, and by the increment dx of the variable, the nth number of factor within the brackets to the function of the cosine is equal 1 divided by p multiplied by integral minus p to p. The limits of the integration, the function which we search the expansion by the trigonometric Fourier series multiplied by cosine of nx and decrement dx, and the bn the factor with the sine function within the term of the Fourier series under the sigma sign, bn equal to 1 divided by pi multiplied the integral from minus pi to pi, the function f at x, f on x multiplied by sine and x, and by dx we have the variable number of the term n, so term within the integrand due to the we consider the integration by the variable x, any variable, maybe time, maybe not. So let's consider the opportunity to have the expansion of the impulse nature control action diagram as a impulse nature of the turning of the rudder with a period from minus tr divided by 2 to tr divided by 2. This is a period. After that, the function repeats. Period is tr, 0, tr by 2 divided, tr, etc. So this function is skew symmetry and odd and skew symmetry. So we can see that the function magnitude, this function is like an impulse, or the impulse nature is skew symmetric due to symmetric relative the point relative, skew symmetric relative the reference point 0, for example here, but skew symmetric and odd. So that's why what mean the skew symmetry of the function means that the function alpha r, the angle of the rudder turn dependence on t equal to the minus alpha r on the t plus minus the period of the rudder turn, if we consider the periodic turning of the rudder, keeping the ship on straight line on course. The shifting angle of the rudder of skew symmetric odd function changes sign when the sign of the time parameter t changes. Expansion into the trigonometric series has a general form. this is expansion into the trigonometric series, the general form, when we assume the impulse nature of the function and its expansion into trigonometric series. We have the standard decision, and we can do the decision ourselves if we just substitute the function into the this integrals, finding the factors for the brackets summands under the sigma sign as in the total of definite considered number unlimited of the terms. Is brackets total is a definite one term indicated n, zero term, and any other, and all others we can consider ourselves and define by the decision of these integrals having this function. This function is constant from 0 to t r divided by 2, and from minus t r divided by 2. This is a symmetric function. So we can this interval of the integration minus pi to pi divide into two intervals, and we will consider this integral as a total of two integrals, etc. So we can do that ourselves. But on the other way, this is the impulse function is appropriately standard, and we can consider this as the total of the considered expansion. So the substitute instead of the function of the impulse nature considered here, we can find in the type of the trigonometric Fourier series. This will be the total factor to the sigma function from 1 to n. And next we consider the definite sequence of the numbers of the term in the expansion into the Fourier series. The first factor under the sigma sign means that just only we consider only odd numbers, 1, 2, 3, 5, 7, etc. of the Fourier expansion, trigonometric Fourier expansion, Fourier series expansion of the function. Due to this function is odd. This is for odd functions. As we have, for example, the number n, given the minus 1 power to n minus 1, or given the minus 1 power to n just 1 positive. So the numerator magnitude can be 0 or 2 if it is 2 divided by 2 in denominator. So this total factor can be just 0 or 1 divided by n, independence on the number of the term. For the fourth term, this is, for example, 0 for second is 1 divided by 2 is 1/4, etc. So we have the sequence of the expansion of the terms in the definite appropriate. We have only the odd terms in the expansion of the function into the Fourier series. This is for the function skew symmetric. And we can find the expansion for the first 9 terms. This expansion looks like the total, the factor for the total for the numbers of the expansion terms 1, 3, 5, 7, 9. We can find the expansion of the angle of the turning of rudder is equal to the factor 4 divided by pi multiplied by the amplitude of turning of the rudder, alpha Rm, and multiplied by the sequence of the functions sine of the frequency of turning of rudder. The frequency of turning of rudder we can find here as a 2 by pi divided by the period of turning rudder. Period of turning rudder we have here as from minus t r divided by 2 to t r divided by 2. This is period of the rudder turning. And we consider the periodic unlimited process of turning rudders for the same maximal angle. We looking for the expansion into the Fourier series to have the differentiable function on the right side of the inhomogeneous equation, to have the decision of the of the ship motion when it rather turns by the impulse nature. And the second is 1 divided by 3. This is a factor multiplied sign, only signs we have. The odd function sign as a cosine is not odd, is a symmetric function. So 3 product by the frequency of the turn rather than the t variable, etc., 1, 5, etc. And we can see, so we can find so many terms as we have to have unlimitedly. But when we substitute this all into the considered expansion of the angle of the turning of the rudder, so instead of this one impulse nature the type of the diagram of the rudder angle turning on time dependence, we have almost the same, but we can see this is a first impulse, the second impulse, and next unlimitedly. So the expansion in the Fourier series means the approximation of the function within the considered period of the variation of the function, and repeated periodically this approximation for all the axes of the variable. So, and this approximation by the solid line we have here indicate the total sum of the expansion of the angle of turning of the rudder by impulses. And each of the summands within the brackets here we can see by the thin solid lines, but the bold solid line we can hear as the approximation of this function of the impulse nature. And so if we have the function of the impulse nature, we can find the function of the expansion in the trigonometric Fourier series of the function of the transverse force arising when we turn the rudder. The transverse force dependent on the angle of the rudder turn is equal. We got this in the considering the issue in the article 12.9, where we consider the keeping the ship on straight course when the action of the controls we substitute by the trigonometric function of the variation. Here we consider the impulse function of the controls action. I mean the turning the rudder control action we consider here as the impulse function. In the previous one, article 12.9, we considered that as the sinus type of the turning of the rudder, keeping the ship on course. This was the simulation of the action of the control system, could be the feedback control system. So for the previous article, we got that the transverse force independence on the angle of the turning of rudder depends like 2.25 multiplied by the mass density of water. For the ocean water is 1.025 ton per cubic meter for salt water multiplied by Vx, the longitudinal velocity of ship. We consider a constant deciding the two equations of the ship motion on the surface, so we consider the longitudinal velocity constant of ship, and this is squared multiplied by the area of the rudder and multiplied by the this all is the function of the expansion of the function of the turning of rudder. This all. So this turn rudder function expansion into trigonometric series in the general form we consider here as the last one factor in the dependence on the transverse force on time, because this function as a trigonometric expansion in the trigonometric series is the dependence on time. So this in sine function within the terms of the trigonometric Fourier series is a time dependency. All others dependent on the angle of the turning of the rudder, and the turning of the rudder itself is dependent on time. So for decision of the inhomogeneous equation, we have to consider the dependencies on time, because we consider the motion of ship on the surface of the water, assuming that the longitudinal motion of ship on the water is of the constant velocity, and the transverse velocity and the rotation velocity of ship in the associated with the ship coordinate system, we consider as variables subject to find. So we can a little bit this is a question for just only one term. So this is for the total total of the expansion and trigonometric series of the transverse force. This is only one term of this expansion. The same as, but with not the sigma sign as well, and the n is variable, because we associate the n, one of the indexes of the transverse force. So this is just a term of the expansion of the transverse force. So we consider the transverse force as expansion itself, due to we consider the turning of the rudder angle as an expansion. This is amplitude of the turning angle. This is an expansion of the non-analytical type of the assigned impulse nature type of the control action by turning the rudder by the impulse type dependence on time. And that's why if we substitute the impulse, the action of the controls by the expansion, so we will have the force as an expansion in the trigonometric Fourier series, redefined by the trigonometric expansion trigonometric series of the angle of the turning. And this is just a type as it looks like the one term of the expansion of the transverse force into the trigonometric series of Fourier. Or we can a little bit simplify this formula by the combining the factors together, as one factor is Cn, and the factor not dependent on time. Cn is dependent only or independent on time, and just the constants for all the terms of the transverse force expansion into the trigonometric Fourier series. And the two factors, only last one factor, dependent on number of the term in the expansion into the Fourier series. And this factor Cn, independent on time, dependent on the number of the factor. In the Fourier series, we multiplied by sine of the angular velocity, angular frequency of rudder turning, the number as well of the term of the expansion of transverse force into the Fourier series and time. So this is just a little bit a simple description of this one term. And besides for use in the differential equation, like here in homogeneous linear differential equation, second order relative, the angular second order for the finding the angular velocity of the ship rotation around the applied axis, we say ship yaw. To have that equation, we have to have one, the substitute of the transverse force when the rudder turned by the impulse function, and we do this by the expansion of the rudder turn function into the Fourier series trigonometric, and the same we have the expansion of the transverse force in the trigonometric Fourier series too. And besides, we have to have the rotation moment around the applied axis as well, the first derivative. by time. We can have this having the expansion in a trigonometric series of the transverse force, and assuming that the transverse force applied to rudder at the ship stern with the arm of minus L2 between the point of the application of all other forces we assumed for the symmetric ship right near the middle of the ship, the forces applied to the ship hull, the submerged part of the ship case. And with this arm, in having the expansion in a trigonometric series of the transverse force, we can have the term of the expansion of the rotating moment around the applied axis with this arm L divided by 2 minus. Having the expansion of the transverse force. We did that, and after that we can find the first derivative by time of the sine. We have cosine and etc. Minus remains. So then we have the second transformed equation from the system of the equations of the ship motion on the surface after the exclusion of the first one equation, because we assuming in the associated with the ship coordinate system Cartesian that the longitudinal velocity of ship when it keeps on the straight course not depends on time. So the first equation we not consider, only the second, the third, and the third equation of the remaining two, we say second equation. We have in the type indicated on the slide, and this when we substitute the first derivative by time of the moment rotation and in the type of this function is non-analytical because we have the angle turns by the impulse nature of the function dependence on time. That's why we have the transverse force as a function of definite impulse form as well as dependence on time, and as well we have the expansion. We did the expansion in the trigonometric series to make it possible to use at the right side of the equation here with the possibilities of each integration and differentiation. And as well, we have the turning moment as well as the expansion of the naturally the impulse nature of the turning moment due to we have the impulse nature of the rudder shifting and shifting. Yes, we have impulse nature, so we have the same impulse nature of the turning moment. And we have all that and the impulse nature of the first derivative as well we have. This is periodic functions. But instead of that all, we use these expansions into the trigonometric Fourier series. We can next substitute this all and y. Instead of ny, we can substitute the expansion, and instead of m z, the rotating moment first derivative, we can substitute the expansion in of the maybe of five terms of the not all five odd terms like first terms, third, fifth, seventh, and eighth. In ninth term, we can substitute the expansion of this consisting of these terms of the expansion of the derivative, the first derivative by time of the turning moment. Finally, we will have the differential equation on this one by the substitute of the expansions instead of the functions on the right side. We have to use expansions due to the expansions in the trigonometric Fourier series are differentiable, are the integrable. But these functions are not differentiable and integrable due to they are of the impulse nature with the bricks of the function. So the bricks of the function is indicated here. So instead of that, we have the substitute by the Fourier series expansion. The Fourier series is differentiable and integrable, and we next have the decision. And the decision of this inhomogeneous equation generally consists of the, as due to the Cauchy problem, consists of the general decision of the appropriate homogeneous equation with assuming that the right side is 0, and the particular decision of the inhomogeneous equation. If assume that the type of the decision of the inhomogeneous equation is like the type of the right side of the inhomogeneous equation. But this homogeneous equation decision will attenuate gradually due to damping of the oscillation. So we have only the self-oscillations due to action of the control system with the right side. So this decision of this equation in homogeneous will be only the particular decision of this inhomogeneous equation, and the general decision of the appropriate homogeneous equation with assumed here 0 reduces them gradually to 0. So it's not relevant to consider the decision of this inhomogeneous equation for the stationary process. Stationary process is a very long time process which not depend on the initial conditions. This decision of this equation will not depend on initial conditions because ship keeping on course is a very long process, and it not depends on the initial conditions. Only the inhomogeneous equation particular decisions is a subject of our interest. And this decision will look in the form indicated here. This is a term of the expansion of the angular velocity into the trigonometric series. This is a term. But we have just simplified the type of this equation. So we derive the common factors and they substitute the denominations, substitute the designations. Instead of this total grid, we use the designations Pn. We can see here this is a fraction, and we have C, and the coefficient here got previously. C and the coefficient here, yeah, no dependent on time coefficient here of this function of first when we define the term of the expansion of the Fourier series of the transverse force. And in numerator we have the factor not dependent on time. In denominator we have the subtract of the minuend of the subtrahend. Subtrahend and the minuend and subtrahend came from the equation we have the transform second equation of the system of the equations of the ship motion on the surface for finding of the angular velocity of ship rotation around the vertical applied axis. The second factor within the brackets of the term of the expansion of the particular decision of the inhomogeneous equation into the Fourier series, this factor Q and we see is a product minus omega r is a frequency of the turning of the rudder multiplied by n, and as we consider just only term. This is a term of the expansion of the particular decision of an homogeneous equation. And this is for the term, we have the second index n, number of the term. So it is within the factor, here in the formula is a factor inside the formula, and the length of the ship divided by 2. This comes from the determination of the rotation moment. And the factor here, nu Vx, is just only constant assigned and is not dependent on the number of the expansion, and not dependent this one factor, and not dependent on time. It's only multiplied by the sine function dependent on the number of this term of the expansion of the particular decision of the inhomogeneous equation, or this inhomogeneous equation when substitute in central functions mz and ny, the expansions in the Fourier series, and we have the decision of this inhomogeneous equation in the form of the Fourier series, and the factor and the term in this Fourier series of the particular decision of inhomogeneous equation is look like here with the factors indicated below. And let's consider, please, the exercise. The elements pulse shifting of the rudder is 0.1745. This is angle of the rotation, dependence on time. So we rotate for port side and for starboard side for 0.1745 radian. This is like for the amplitude of rudder turns degree is equal to 10 degrees. So this amplitude, if you consider 10 degrees on the left side, we turn the rudder. On the right side, we turn the rudder for 10 degrees. This is equal to 0.1745. We indicate this just a little bit simplified, as exactly we understand that the pulse shifting of the rudder, we have no analytical dependence, and this assume that this is the maximal magnitude in the radian. But actually, we have only the continuous dependence as the expansion of the rudder turning into the trigonometric Fourier series, as we did, yes, as we did here, but is, oh, sorry, as we did here, but it's, but this type of the equation is complex. Here we just indicated initial data for the exercise as simplified designation. This is period of the rudder turns, 30 seconds, half a minute. The characteristics and particulars of ship: length of the waterline 46.2, breadth 10.5 meter, average draft of the load line T 4.37 meter, the coefficient of overall completeness of the hull, that is the ratio of the submerged volume of ship hull to the volume of the parallelepiped with the sizes of the ship, L breadth and the draft. This is a coefficient of completeness of midship section. This is the proportion of the area of the submerged transverse section of the ship to the area of the rectangle with the sizes of the ship breadth and draft. And the coefficient of completeness of waterline area is the proportion of the waterline area to the area of the rectangle with the sizes of the ship length and breadth. And the coefficient of longitudinal sharpness of ship is the fraction of general completeness, overall completeness factor to the coefficient of completeness of midship section, 0.7. So this is particulars of definite one ship. This is looks like the industrial fish catching ship of the middle size. The ship velocity is 12.7 knots, is equal to the 6.53 meter per second. Displacement of the ship 1,228 ton. Area of the rudder blade is just 1/50th part of the area of the ship section by the diametral plane. The diametral plane section area is about ship plane's product to draft divided by 50. We have the rudder area 4 meter. As well, we can have the added masses of water and moments of inertia by empirical formulas. We got it in the articles at 12.9. As well, for the other ship, the formulas, empirical formulas indicated in the article 12.2. And this is finding for this definite one ship. We did that in the article 12.9. And this is the impact of the water inertia onto the ship motion with acceleration along the longitudinal axis associated with the ship axis X. And this is added masses of the ship translational motion with acceleration along the transverse axis Y, ordinata, and Z. Z is applicata axis, the translation motion, the added characteristic of the water inertia to the ship is 850 ton, we got in the previous one article 12.9. The moments of the inertia of ship, characteristic of the inertia, rotation moment with acceleration around the transverse axis of ordinata y and the vertical axis around the vertical axis yaw. The own moment of the inertia of ship is 122,667 ton by square meters. This is as well by empirical formulas indicated in the article 12.2. And edit masses, this is edit moments of the inertia, the impacts of the water inertia on the ship inertial characteristics when the ship rotates with angular acceleration around the vertical applicate axis and the transverse horizontal ordinate axis. So these moments of the inertia got as well by the empirical formulas. They are 45,610 ton by square meter. So when we substitute this all into the finding of these factors, Pn, Cn, Qn, V, X, etc., we can find the term of the expansion of the particular decision of the inhomogeneous second order linear equation of the ship motion as the expansion of this decision into the trigonometric Fourier series. And this is a term of this expansion of Fourier series due to the control actions used on the right side of the inhomogeneous equation. We have as expansions in the Fourier series as themselves. They are not the analytical functions available to have the derivatives or integrals on that. And the constants are here, nu, Vx, etc. We have 1 point. It just continuous of finding the data process and the finding the elements of the motion independent on time as the factors. And this is the cyclic velocity of ship rudder turns on the left, on the right. This is the same cyclic velocity as we considered in the previous one, article 12.9, for the sinusoid type of the function of the controls. I mean, the rudder turn sinusoid types with the same cyclic velocity as considered a show we do for the impulse nature of the rudder turns with the same frequency. But in the previous one article, we consider this in the type of the function of rudder turns, as which was the sinus type. Here we have the impulse type. Expanded into the trigonometric Fourier series and substituted by many trigonometric functions terms. Cn, we got the independent on time part of in the formula of the term of the expansion of the transverse force and the trigonometric Fourier series. There we have two factors in the designation of the two factors, and one factor is designation of the term of the expansion of the transverse force into the trigonometric Fourier series. The first factor is Cn, and the second dependent on time sine function with definite frequency and the number of the term in the expansion. And Cn is just a constant, and Qn is a factor here dependent on the cyclic velocity of the rudder turns when keeping the ship on the straight line, when we simulate the action of the control feedback system of the ship. This is dependent on the number of the term of the expansion, the trigonometric series of the factors. So it's Qn we have here for n equal to 1, 3, 5, 7, and 9. So we consider n equal to 1, 3, 7. We can keep, but the accuracy of the approximation by use of the trigonometric Fourier series dependent on the number of the considered terms of the expansion into the series impacts the accuracy of the approximation of the periodic process of rudder turns. This impacts the accuracy as when we use other approaches like the numerical method of the decision of the differential equation. So the impacts on we using the numerical approaches to find the decision of differential equation. The impact on accuracy has the just magnitude of the step of the approximation and the number of the steps. Here we have the impact on the accuracy of the number of the considered terms of the expansion of functions into the trigonometric Fourier series. To determine the diagram, so for example, this diagram of angular velocity, when we substitute the angular velocity by the expansion to trigonometric Fourier series with definite factors to each sum, and so for the first we have 1 of course the factor here is the fraction 1 and 2 1. Here 1/3, 1/5, 1/7, etc. And we consider this all others in the type we got here, but when we substituted the factors, these factors with the elements of the particulars of ship and the elements of it, characteristics of the inertia, etc. When we got this all substitute here, using the Excel program, we can find that the terms of the expansion of the particular decision, this particular decision of general particular decisions of the inhomogeneous equation of particular decision of this inhomogeneous equation when we substitute the controls here, the functions of the control on the right side by the expansion, the trigonometric series. And for each of the term of the expansion of the angular velocity of ship rotation around the applicate axis, that is a yaw, and the action of the ship controls, we can see on the diagram the definite, many diagrams here, dependent on what is the term of the expansion we got of the particular decision of the inhomogeneous equation, differential second order linear equation. And this done each sum by thin, but by the thin line, by thin solid line with a definite designation of the term. And the total we have by the bold solid line here. This looks like almost sinus type of the dependence of the rotational velocity on time when we have the impulse turning of rudder. Nevertheless, after the substitute of this turning of rudder impulse of the impulse nature by the expansion in the Fourier series with the total indicated here by the bold solid line, and after the substitution of the equation we got after the substitute of into the equation of a differential equation second order inhomogeneous linear equation, we got the expansion of the particular decision into the Fourier series, and they was indicated by a bold solid line. Looks like very sinusoid with not the breaks of the function. And next we have to have another element of the motion as the transverse velocity. And let me please remind that as the angular velocity, then the transverse velocity, we looking in the um, associated with the ship coordinate system Cartesian. So this is the expansion of the derivative, first derivative of the translational velocity along the transverse axis. That is the translational transverse acceleration of the ship on the water surface, the first derivative of the velocity transverse. And this expansion of the velocity as a decision of the indicated equation. This was the first equation after the simplification of the system of the equation of strip motion on the surface of calm water. We considered them in details in the article 12.5. So instead of this, due to we have the control action. Here we have the control action by the assigned by the transverse force, and here we have the previously got decision of the angular velocity of the ship motion on the surface under control. Got here the expansion into the Fourier series, and we had the expansion into the Fourier series of the transverse force and why we got it even before having the decision for the angular velocity. We had this before to have the decision of the angular velocity, everything into the form of the Fourier series. And we next find the expansion into the Fourier series of the first time derivative of the transverse velocity, that is transverse acceleration of the ship motion on the surface. This consists of the substitutes of the terms of the expansion of the transverse force. For example, this one. This is this is a transverse force term of the expansion into the trigonometric Fourier series. We have here this one. This is the n, y, and the term of the expansion into the trigonometric Fourier series of the transverse force of number n. We have here as a first summand, the first summand that we have. And of the next we have delta the displacement of ship plus the moment the added mass of the water when the ship moves with acceleration in water along the abscissa axis. Yes, we have the constant longitudinal velocity of ship. We have next all that we have. This is the expansion of the angular velocity into the Fourier series, just one term. So term number n. So term number n of the transverse force, term number n of the expansion of the angular velocity. So we can find by the integration of this term the expansion transverse velocity into the trigonometric Fourier series with derivatives and derivatives where argument interval plus minus p divided by 2. So we can use the property of the functions, of the periodic functions, that with not the formal the integration of this function, we can find what is the integral of function. With not doing the mathematical transform of the integration. Why? Because for the trigonometric functions, they are corresponded of the phase elements as the transverse velocity, transverse acceleration, maybe transverse displacement. They are derivatives or anti-derivatives to each other, and if they are trigonometric functions for the with not the constant of the integration, just the trigonometric functions with not the exponential factors dependence on time, not the trigonometric functions as for the particular decision of the inhomogeneous equation. So we can find that the velocity have the factor of the scale, because this factor of the scale, when we do the integration, this comes from the argument of the cosine and sine functions. This comes to when we having the derivative, we have to to derive this ahead of the function, this factor to the time inside of the sine and cosine functions, but as well having the to find the antiderivative, we have to divide for this factor. And besides, we would remember that instead of sine, we will have having the minus cosine, having the antiderivative, etc., for each trigonometric functions, and they are independent, the same, but we can just use the difference of the phase, minus pi divided by 2. So the cosine and sine functions are about the same, but they have the phase shift by the abscissa axis when we assign the abscissa axis in the units of pi, when we consider the abscissa axis as the periods of the oscillations. The sine and cosine functions, which are derivative and antiderivative to each other, but they are with the shift in the phase minus p2. So when we want to of the derivative find the function, the zero derivative, which is antiderivative to the relative to the function of derivative, then we have to divide by this factor to the time under the argument of the function, and we have account the phase difference of the derivative and antiderivative of the sine and cosine functions. The phase difference is minus p divided by 2, the constant phase difference. So having this decision with not doing the technical mathematical transform, we can find the diagram of dependence of translational velocity transverse on time under the action of the originally assigned impulse nature of the rudder turns impulse, the periodic nature of unlimitedly repeated impulses of the turns to the sides, to the port side and to the left side turns of the rudder. Finally, we had the expansion into the trigonometric Fourier series of the angular rotation around the Foucault axis. This looks very sinusoid with not the breaks of the function. This is almost analytical, the consistent of the terms, each of which is the sinus or cosine function on time. And for the translational velocity decision, this equation of the which we had originally as a first equation after the simplification of three equations of the ship motion on the surface of the still water. After the integration, we did not do this integration. We just only used the functions, use the geometric properties of sine and cosine functions. And if we have the expansion into the sine and cosine functions, we no need sometimes to do the integration itself. We can only use the properties of these functions due to the difference of the phases of sine and cosine, and due to the other scale between the variable and between the function and its derivative of a derivative that is zero derivative, the function itself. So we have the expansion into the terms. This thin solid lines, we designate these solid lines as the terms of the expansion of the translational velocity into the Fourier trigonometric series, and the bold solid line we have the total of the expansion of the translational velocity in the trigonometric Fourier series. This is bold solid line. It looks very sinusoid. Looks very sinusoid here. After that, we have to find the transverse displacement and angular displacement. Here we find in the transverse displacement. Transverse displacement of ship motion, the individual terms of the expansion into the trigonometric series have the same scale, 1 divided by cyclic velocity of the angle of the rudder turns, product by the denominator, and the phase correspondence minus pi divided by 2 with respect to transverse velocity of ship kept on course. So having the equation of the ship velocity kept on course, like here we have this equation of the ship velocity, this with expansion of the velocity, and this corresponds to the expansion of the, this is a term of the expansion of the translation acceleration in the transverse direction. This is translation acceleration term, this is the transverse velocity term, and having the transverse velocity term we can find using the same property of the sine function. When we differentiate it and integrate the function, we have the factor ahead of the function, or the factor or the denominator, and the shift of the phase, the phase corresponds minus pi divided by 2 with respect to transverse velocity of ship kept on course. This also means the ratio of the transverse displacement y of ship motion on scale divided by omega r and the n number of the term of the expansion, which is the Fourier series squared in the denominator, and phase shift minus pi to the derivative. So if we do transform the got function of the derivative, this is a term of the expansion of the derivative of the velocity, we can have this expansion of derivative velocity just immediately we can find the displacement, having the properties of the sine and cosine functions when we differentiate or integrate sine and cosine functions having cosine or sine. And this is the dependence of the term and term of the expansion of the translational displacement, the dependence on the having the term of the function of term of the translational acceleration transverse into the expansion of the this derivative into the expansion into the trigonometric Fourier series. So, and then after the substitute, we have the term of the expansion of translational displacement into the Fourier series. Having this formula, we next with transform with the phase correspondence minus pi with the extra the factor ahead of the brackets of the finding when brackets of when finding the term of the expansion of the translational velocity. And having this formula, we can find with the we can having the factors of the expansion of these terms into the total of the Fourier series. We have the diagram, the bold solid line is a total, and designated by the y5, y7, y9, etc. The terms of the expansion, the thin solid lines, terms of the expansion of the translational displacement into the Fourier series. Okay, one more question I have to consider. Actually, we did decide. We have the translational displacement and we have the translational velocity. That's what we have to find. The keeping of the ship on course by the controls assigned of the impulse function of the rudder turning. We have that the motion of ship not looks like impulse, but looks very sinusoid, like sinus or cosine functions, etc. So this due to considering the own properties of ship, which just transforms the impulse nature of the controls action into the smooth nature of the ship motion elements. The ship transfer displacement when moving under the influence of periodic impulse rudder shifting. Yes, the question arises, what could be if the ship lose the control of when moving along the straight course? The ship will go into the steady circulation if the kinematic energy of ship replenishes by the work of the propeller or by the other drives. The steady circulation radius is r, the velocity of ship, the longitudinal velocity associated with the ship coordinate system, divided by the angular velocity of the rotation around the applied axis. The empirical formula we have for determining the radius of steady circulation, this empirical formula is 3 multiplied by ship length multiplied by diffraction, length minus breadth divided by length plus 3 breadth, or by the relative value of the same if we divide both sides by ship length, the relative radius of circulation is like this formula. The relative radius of steady circulation for the relative length of ship, L divided by B, so we have the relative length by B in the range from 4.5 to 9 to 0 of this relative length by ship. So this relative length of the ship is what is the relative radius of the ship's steady circulation. So if the ship do not possesses the property of the sustainability of the straight motion on the surface of water with no action of the controls, on the same time the ship usually possesses the property of the motion by the steady circulation when losing the sustainability on the straight course. The ship obtains the circulation mode of the motion with a steady radius, here indicated as a property of the ship itself, got by the empirical formula. The highest angular velocity, which could be considered the limit in rotation velocity, which corresponds to the real number of roots of the considered characteristic equation. So when it loses, the ship loses the sustainability of the motion, depending on the relative velocity got by the transforming of the empirical formula is. So considering this formula, we can find what is the highest angular velocity. This angular velocity, and this is the variable the same, L divided by V, relative length of the ship, the proportion of the ship length to its breadth. And we have the parameter of the diagram. The parameter is the length divided by the relative velocity of ship. So for how long ship goes its length. For 10 seconds, for 20, for 50 seconds, etc. Is smaller the velocity, the bigger is the smaller is the, excuse me, yeah, this is the opposite. As slower the ship, the bigger the denominator. The slower the ship, the lesser the denominator. So the bigger is the maximal angular, highest angular velocity of the ship rotation in the steady circulation. Questions and comments. The use of the composition of ship's control function, the rudder, shifting or using another control device to determine the elements of ship motion under the control. For example, the elements of movement of ship when keeping it on course, take into account the premise of or assumption of time repeatability of control function, the control efforts of the rudder shifting angles patterns outside the limits interval of control function expansion to the trigonometric series. If we consider the ship keeping on straight course, usually with the use of the control system, with no feedback, we can substitute this by the simulation of the periodic function. This periodic function can be as, for example, the trigonometric function of sine or cosine, or the combination of sine or and cosine. And the very fruitful can be the substitute of the non-analytical nature of the control function. For example, the impulse nature of the control function, which of the function with the breaks, with not continuous function, with not smooth function. We can substitute by the trigonometric series, because trigonometric series for the non-analytical function, the series, the expansion into the series for a definite number of the terms of the expansion is suitable to find the derivatives and to find the antiderivatives for integration and for differentiation. 12.10.2 mathematical form of trigonometric Fourier series and determination of the coefficients of the expansion to the trigonometric series. The odd functions, the skew-symmetric functions, expansion of an odd and skew-symmetric periodic function into a trigonometric series. The Fourier trigonometric series is the total, the sum of definite number of the unlimited number in general approach, but actually the definite number could be the big number of the terms of the expansion into the Fourier series, and each term looks like the brackets, and within the brackets we have the two functions, two summands. The first is the summands of sine and cosine functions, and with the factors, definite factors for the sine and cosine functions. And these factors for sine and cosine functions within the brackets for each term of the expansion of the function into the Fourier series we can find by the integration of this function multiplied by psi or cosine within the interval of the integration from minus pi to pi. This is just a usual approach how we can approximate the function by the Fourier series. This is for the usually for the periodic function. That is one of the assume that out of the interval of the approximation, the function periodically repeats, unlimitedly repeats with a considered period as considered as the interval for the approximation by the Fourier series expansion. 12.10.3, the use of expansion of function into a trigonometric series with which terms can be integrated and differentiated for the numerical integration of equations which include a function expanded into this series. Sometimes if we cannot integrate or differentiate the non-analytical functions, maybe the functions of the impulse nature, as it could be for the controls of ship when keeping the ship on a straight course, we need to expand these functions into the series, for example, of or just approximate by any analytical function, or expand this impulse function into the series of terms which are analytical functions suitable for differentiation and integration. 12.10.4 methodological difference between solutions of differential equations found by methods of numerical integration are dependent on initial conditions, and the solutions could by expanding parts of the equation, namely the right side, into trigonometric series within the framework of the premise or assumption that beyond the interval of series expansion, the simulated function is periodically repeated, which usually matches good the functions for stationary processes. Indeed, the control of ship when it's keeping on the straight course is a stationary process. The stationary process, which usually very long process, not dependent on the initial conditions. The impact of initial conditions gradually damped due to the damping forces, for example, or moments. And in this case, for the stationary process, we have to consider the nature of the control process as periodic. because the alternative is only if the process, if the function is non-stable, unlimitedly increased or reduced, and only one remains the approach that the processes have to be periodic, and that when this periodic process is not of the analytic nature from the mathematic point of view, then we have to, this is very fruitful to substitute this dependence of the controls on time, of the control actions on time. We can substitute by the trigonometric Fourier series, which we can, each term of the series, we can differentiate or integrate. This could be the suitable to find the decision of the particular decision of the inhomogeneous equation of the ship motion in particular. 12.10.5 elements of the trajectory that are stationary in nature, independent of the reference time, of a ship held on course by periodic shifting of rudder by a feedback control system with a linear transfer function and with limited performances speed. Usually, the control system have the linear transfer function and the limited performances of the action of the control system. And any other discrepancies can be which cause the delays in the action of the control system. That's why we cannot keep the ship strictly on the straight line. That's usually, instead of straight line, we have to keep the ship with definite deviations as small as possible when it moves. But this trajectory are stationary in nature because it very looks like long time periodic deviations look like the periodic function, so like the expansion of periodic function into the trigonometric series. We can use this for the research and study of the processes of the ship control when the ship keeps on the straight course. 12.10.6 finding the elements of motion of a ship using a trigonometric series, expansion of the function of periodic pulse turns of the rudder, which linear transfer function with linear transfer function, the sensitivity threshold and performance is speed limit. Simulating the feedback control system can be specified analytically in a table, graph or by along the algorithm, etc. Yes, usually we consider the linear transfer function is due to when we assume that we have the control system with the feedback, which is usual is maybe the instrument control system or just action of the pilot of ship which observe the element of the ship motion, like the course, like maybe the accelerations of ship transverse acceleration or acceleration observed by the sensors. Then, due to the available sensitivity threshold of the observing system and due to the speed limit of the action of the control system, we cannot obey the strict motion of the ship along the straight line. Actually, it was the deviations that looks like the definite periodic process. The trajectory is of the periodic type. 12.10.7, the more accurate perhaps than theoretical impulse model of the rudder periodic shifting, which has mathematical discontinuities. It is the approximate description of trigonometric series, which terms are smooth, continuous, and differentiable functions. Due to the abstract approach, when we substitute the action of the ship controls by the dependence of action of the controls, like of the impulse nature, this corresponds to the use of the function with the brakes. In practice, we have no the functions with the brakes because due to the any gaps in the system, delays and the gaps in the system of the control, delays of the action of the system, and the gaps of the mechanical system of the ship's control. Actually, we have the more smooth dependence, more smooth as differentiable, and perhaps the theoretical impulse model of the rudder periodic shifting is less accurate description of the action of the control system than the expansion of the impulse model of rudder periodic shifting into the trigonometric series. The expansion could be more precise description of the action of the controls. 12.10.8 terms of expansion into a trigonometric series of functions. The transverse force on rudder and the moment from the transverse force turn the ship relative to the point application of relative forces to the center of the gravity approximately correlated with the origin of the coordinates under assumption of ship symmetry with respect to coordinate planes. The terms of the expansions, to find the terms of expansions, we use the dependence of the transverse force arising on the rudder when it turns. So we assume the linear nature of the force arising on the rudder when it turns to the side or to port side or to the starboard side. So, and with users and finding the expansion to the trigonometric series, first we have the expansion of the transverse force, considering that as a dependence of the factors independent independent on time. These factors like, for example, the translational longitudinal velocity of ship along the longitudinal axis squared in this formula, finding the transverse force on the rudder, and considering the area of the rudder, considering the mass density of water, and considering the next factor is the coefficient of the lifting force arising on the rudder when it turns. And this dependence of the transverse force on time depends dependence is due to the dependence of the angle of the rudder turn on time. So if we have the expansion of the pattern of the rudder turn on time, if we have the expansion of this function into the Fourier series, we can have a substitute that into the formula for the transverse force to the determination of the coefficient of the lifting force arising on the rudder. We can find the expansion of the transverse force. After that, having the dependence of the transverse force, of the rotating moment of the ship on the transverse force, with the arm of the minus length of ship divided by 2, as assuming that the distance between the point of the application of the force on the ship is around the middle of the ship, and the point of application of the transverse force on rudder is the location of the rudder astern. So the half of the length below behind the point of application of the forces on the ship. Assuming that we can have the expansion of the transverse force, we can have the expansion of the rotating moment. That's all we use in the right side of the inhomogeneous equation of the ship motion when finding the angular velocity of its rotation around the applicate axis. 12.10.9 determining the terms of the expansion into trigonometric series of the function, the angular velocity of ship turn, the transverse translational acceleration, the transverse translational velocity in ship motion, transverse displacement by integrating the differential equations, the elements of which are terms of expansion into the trigonometric series of the function, the lateral force on ship rudder blade and the moment and the lateral force on the blade. We have the type of the decision of the angular displacement of ship due to the use of the differential equation second order in homogeneous equation. This decision depends in a great degree on two summands. The first summand is due to the Cauchy problem. So first summand is the general decision of the appropriate homogeneous equation with the right side of the equation equal to 0, and the second summand is the particular decision of the inhomogeneous decision with the assigned controls on the right side of the equation. And if we have the expansion of the controls into the trigonometric series, we will have the type of the decision of the we will have the type of decision, or particular decision of the inhomogeneous equation. This is important for us, the inhomogeneous equation, particular decision due to the general decision of the considered homogeneous equation gradually reduces to 0 due to damping of the ship motion on the surface of the water. That's why if we have the right side of the equation as a type of the expansion of the non-analytical functions into the Fourier series, that's why we will have the decision of the particular decision of the inhomogeneous equation as the expand as its expansion of the decision particular of the homogeneous equation into the Fourier series. 12.10.10, the form of terms of expansion into a trigonometric series of functions of ship control efforts, which particular solutions of the differential equation for keeping a ship on course are sought. Constituting of solutions of set to the equation the linear combination. Yes, the particular decision of the inhomogeneous equation when the right side of the inhomogeneous equation assigned as the expansion into the Fourier series of the non-analytical, of perhaps non-analytical type of the controls. This leads to the decision, to this particular decision of inhomogeneous equation as a superposition of other decisions. So we consider, formally we consider the motion of ship as a superposition of many motions. And the right side, if we, right side of the inhomogeneous equation, if we consider the right side as the superposition of other control actions, which gives us as a total the expansion of the function of the control. That's why the decision, the particular decision of the inhomogeneous equation got as the expansion into the Fourier series summands. The same indicates the superposition of definite number of the decisions of the motions of the ship on the controls. It depends exactly on how many terms of the expansion of the control action to the trigonometric series we consider. 12.10.11, the form of term of expansion to trigonometric series of the function of angular rate of turn of ship held on course by the periodic impulse shifting of the rudder and the form of the coefficients, including the term of the expansion. Actually, the term of the expansion corresponds into the trigonometric series in function of the angular rate of turn of ship. The function corresponds to the type of the decision of the, or the particular decision of the inhomogeneous equation, and this very close corresponds to the right side of the inhomogeneous equation. And if the right side of the inhomogeneous equation is the expansion into the trigonometric series, then the form of the decision of the ship motion element, like angular velocity, will be as the expansion into the trigonometric series. 12.10.12, find in terms of the expansion to a trigonometric series of functions the translational transverse acceleration of a ship held on course, the translational transverse velocity and transverse displacement by integrating differential equation, considering the sinusoidal functions with derivatives and antiderivatives, phase correspondences with the argument interval plus minus pi divided by 2. One of the benefits when we use the expansions into the trigonometric series of the functions of the right side of the inhomogeneous equation, differential equation, finding the particulars of elements of the motion of the mechanical system. One of the benefits is that sometimes we don't need to have technically to find the derivatives and antiderivatives of the phase correspondences. So as when we have, for example, the angular acceleration, next we can substitute by the as a particular decision of an homogeneous equation, substitute by the expansion into the terms of the sine, cosine types, the summands of the terms of the expansion of the right side of the equation. Then we can find all other antiderivatives having, for example, the angular velocity. We remind that if we decide about the angular acceleration, we can know for sure that angular velocity and just the angular displacement. Angular displacement is a change of the ship course. For example, to do that, to find that we have to change the system of the coordinate from the associated with the ship to the constant one, immobile system to find the course, for example. But anyway, the dependencies between the phase elements, which each to other equal to the derivative or antiderivative, for the trigonometric functions as a sine and cosine, we can do very formal with not technical finding the derivative or antiderivative because we know that the type of derivative and antiderivative corresponds to the type of the sine and cosine function with only the phase correspondence. Due to we remember that sine and cosine are the same functions with the argument interval with the phase correspondence plus minus pi divided by 2. We can find sine and cosine functions as the derivatives or antiderivatives of each other. Exactly, we have to have correct this. We have to use correct the phase correspondence. And besides, when we find in the derivatives and antiderivatives of the trigonometric functions like sine and cosine, we adopt that we have to consider the scale difference. The scale difference is due to finding the derivatives. We have to have the extra factor to the derivative as under the sine and cosine functions with the time argument or with other variable argument, maybe x argument for time argument, x argument, etc. This, when finding the derivative, the factor of the argument have to consider the factor of the function ahead of the function into the definition of the derivative. When we do, and we have the antiderivatives, this factor to the argument in the sine or cosine functions, we consider when finding the antiderivative, we consider as the denominator, as a factor with the 1 divided by the factor got from the sine and cosine functions as a factor to the variable. So the differences are between derivatives and antiderivatives of sine and cosine functions, just the correspondence of the argument, and by the scale factor to the function, finding derivative or derivative. So, and to do that, sometimes we need to have the technique to find the derivative itself. We just only use the formal transformations of the good decisions for any of the function. Would it be just function or its derivative or antiderivative? We can next transform in the phase which one we require to have, phase element of the motion. 12.10.13 integral elements of motion of a ship kept on course by impulse shifting of the rudder, the lateral velocity, and the ship motion lateral displacement found in the four linear combinations of the particular solutions, similar mainly to the elements of the motion characteristic and the sinusoidal pattern of control efforts. So, in the previous article 12.9, we considered the motion of the ship under the controls with the pattern of the change of the rudder angle turn with the same frequency as in the definite one, article 12.10. But in the previous one, 12.9, we had the type of the sinus function of the control action, sinus function of the rudder turn. In this definite one, article 12.10, we have the impulse with the brakes of the function, the impulse nature of the periodic function of the rudder turn. But after the processes of finding the elements of the ship motion, like the angular velocity, like the translational velocity under the controls, keeping the ship on the course, the angular velocities and the translational velocities of the ship deviations from the straight course, we found that the decisions of the elements of the ship motion are smooth and continuous and differentiable in both cases. As originally in the article 12.9, when the control actions were assigned as the sinus or cosine function, or as in the article 12.10, when the control actions assigned as an impulse function, impulse dependence, impulse pattern, which we substitute by sine and cosine expansion in the trigonometric series of Fourier of 12.10.14. The overwhelming influence of the first order term of the impulse expansion to trigonometric series and the reduction of higher frequencies influence in the spectrum of the impulse function of the control efforts expansion due to the decrease in scale factors when integrating trigonometric functions depending on the number of series term and the decreasing coefficients of functions expansion in this series inversely proportional to the number of series of term. Yes, the independence of almost independence of the smoothness of the dependencies of the elements of the ship motion, like the angular velocities or translational displacements and velocities, etc., on time, independence on the type of the assignment of the control functions. The control functions assigned, like in the previous one article, as by the sine functions, and here we assigned in the article number 12.10 as the impulse functions, substituted by the expansion of the function into the differentiable trigonometric series. But we have the same, almost the same, where it look like the smooth and continuous decision of the dependence on time of the elements of the ship motion. This is due to the decreasing scale factors when integrating trigonometric functions, depending on the number of series term, and the decreasing the coefficients of functions expansion in the series inversely proportional to the number of the series term. These proportions and these factors of the reducing of the shape of the nature of the periodic comparable action of the controls is due to the reduce of the high frequencies influence in the spectrum of impulse function of the control effort expansion. This due to this we can see by the Fourier approach of the expansion into the trigonometric series and finding the methods of finding of the coefficients in the Fourier approach. This exactly reflects the properties of ship as a physical mechanical system, yes, because this undergo to the concepts of the used mathematical approaches, yes, which describes the physical properties of the ship. This reduces high frequencies influence in the spectrum of impulse function control efforts. That is, so the ship moves more smoothly than more smoothly. I mean, talking about the dependencies of the elements of the ship motion on time, then the control actions are less smooth. It could be the sharp and of the impulse nature, the control actions. 12.10.15, the usual instability of a ship without active keeping on course, which is visible when solving two equations of flat ship motion on water in the horizontal plane. If the characteristic equation has a real number roots, the tendency of a ship to maneuver and turn the move towards the side in the mode of self-oscillation or to enter in a stable circulation if the longitudinal velocity of ship along the x-axis associated with the ship is maintained by propulsor's operation. In one of the previous articles, we consider the ship motion on the surface of still water with not controls, and usually we define that the ship do not possesses the property of stability on course, and it tends to lose the sustainability. It can have, but only in the motion aside to the starboard or to port, to the side. Transverse motion could be stable of the ship within the definite concept of the stability, if we consider the stability as the self-oscillation of ship motion aside. Usually the ship motion along the abscissa axis in the longitudinal direction we cannot consider as a sustainable with no the action of the control system. But the ship, when it loses stability on the stretch course, can obtain, and not can obtain, but obtains the stability in the concept of the stability of the sustainable circulation, if by the action of the propeller or other drives, the kinematic energy of the ship motion along the associated with the ship longitudinal axis, the kinematic energy replenishes by the action of the propeller. Then the ship goes into the steady circulation with a definite the radius of the circulation, and this is what we can have when the ship loses the control on the straight trajectory. To have the control, we have to have the autopilot, or maybe just the pilot as a human person, the pilot acting to keep the ship on the straight course. The feedback system, we can simulate this feedback system by the periodic processes of the ship keeping on straight course, periodic processes of the shifting the rudder or the rotating rudder to definite angle by definite patterns of the control. It could be the impulse pattern or just sinusoid pattern for the technical facilities, like for the autopilot is more characteristic the impulse pattern of the ship control, observing the elements of the ship motion when the pilot or autopilot acts as a control system by the elements of the ship motion. 12.10.16. Determination by the empirical formula of ship steady circulation radius, the circular motion, and in the mode of steady circulation, finding the maximal angular velocity of ship rotation, which can serve as the limit of the theoretical values of the ship angular velocity, got by solving the equations of ship motion with real numbers roots or characteristic equation. finding of the maximal angular velocity of the ship rotation, which corresponds to the minimal circulation radius when it loses the sustainability of the motion along the straight trajectory. For example, with not the control due to this radius of the circulation of steady circulation of ship is a characteristic not of the control system but of ship itself. This finding we can do by the empirical formulas available because the theoretical solution opportunities are limited due to the fact that this solution would be of the non-linear ratio. Non-linear ratios we cannot decide, but we have the empirical solution to find the radius of circulation and the angular velocity of the circulation appropriate to the radius. Thank you.